Hi, let me introduce you with the most beautiful theory in physics I have learned till now, or more specifically in the field of nuclear and particle physics, the theory named quantum chromodynamics. As per the name, you have assumed that it's the theory that relates the particle with the color. Then your guess is absolutely correct. But let me start it from the beginning. Let's dig the history behind it. So when the first quark model is given, there's a silly mistake. I'm saying about that. When the first quark model is given, they are assumed that quarks are the particles which have charge number, baryon number, Strange number, and other things are that. But all that are same for a fixed quark. That is, if you consider an up quark, for that up quark, its charge is 2/3, baryon number is 1/3, lepton number is 0. I'm saying our strangeness number is 0. So for all up quarks, all these numbers are same till the quantum chromodynamics theory is given. So when this was assumed, then according to Pauli exclusion principle, as proton is made up of two up quark and one down quark, the two up quarks can't have the same state. That violates the Pauli exclusion principle. That's some serious problem in it. So to resolve it, the theory of quantum chromodynamics suggests that there is another quantum number, that is color quantum number, is associated with each of the quarks. That is, with quarks there are three quantum number: color quantum number, red color quantum number, blue color quantum number, and green color quantum number. So although all quarks, all up quarks have same charge, baryon number, leptonic number, but they have different colors if they are making a same particle. That is, if in the proton the two up quarks have two different color quantum number, that resolves the problem of Pauli exclusion principle. As the quarks are the fermions, so the two fermions can't have the same state, which violates that principle. By assuming that the two up quarks although have same charge quantum number and leptonic number, baryonic number, but they have different color quantum number. So by assuming this, we can resolve the Pauli exclusion principle and we are good to go with this theory. Now a question must be arise in your mind, that how these three quarks are held together to form the proton or neutron or any hadron particles. According to this theory, they are assumed that there are another particle named gluon, which are exchanged between this quark to bind these quarks. As per gravity, the graviton particles that exchange between you and Earth, that is responsible for the gravitation force between you and Earth. That is same for quarks. But for quarks, the exchanged particles are called gluons. Gluons are chargeless, spin one particle and having the velocity of light. That means gluons travels with the velocity of light between the quarks and bind the quarks together. This field that binds the quarks together is known as quantum color field. And the theory that gives this field theory named as quantum chromodynamics. So now let's talk about some questions based on the information I have given previously. But you must have other information to do those. Firstly, if you denote a quark with a small letter q, then that quark can only have the color blue, green, or red. Similarly, if an antiquark denotes by q and a bar upon that, it can only have color anti-blue, anti-green, and anti-red. Similarly, if you consider gluons by small letter g, then all gluons can have a color and a anti-color, that is green and anti-green. That's a color of a single gluon. A single gluon can have green and anti-green associated with that, and can have blue, anti-blue, red, anti-red. Similarly, can have green, anti-red, green, anti-blue. So dot dot dot, it can have those many number of color that you can arrange with red, with this three color, and with this. So suddenly my phone's storage was completely filled and it did not catch on my eyes. So let's start from beginning. I have said that this number of arrangements are possible with these three color and these three anti-colors, and those colors can have a single gluon. So now if a quark denotes by a small q having the color B, that is blue, emits a gluon in the color blue and anti-red. That is, if a gluon emitted from a blue quark, then the quark became red. So this type of question is asked in the exam. If you have not learned this process, again I am repeating another example. Suppose you have this red quark Q with color red, and this red quark emits a gluon having color red and anti-green. So this quark emitting and gluon having color red, so this red will be vanished, and the color of the quark that is produced will be the anti-color of this anti-color. The gluon have anti-green, so the new quark will have the color green. So this is the process, and this type of questions are asked in some competitive exam or some other exams. So get prepared for this, and other things are there to learn in quantum chromodynamics, but I think it's enough for you and also for me to this much for quantum chromodynamics. As here a gluon is emitted from a quark, similarly a quark can absorb a gluon. That is, let's say a quark having color green and it absorbs a gluon. I am representing gluon in the form of this wave form. So the gluon have let color anti-green and red. By absorbing this gluon, this quark having color green become a quark of color red. So if a quark having color green absorbs a gluon having color anti-green and red, the quarks become red. Similarly, if a quark having color red and absorbs a gluon of color anti-red and blue, that quark became blue. So these are the possible arrangements, or these are the possible things that can be happened with quarks and gluons. So in previously I have said that these quarks are bind together by this exchanged particle named gluon. So when these gluons are exchanged between those two quarks, the quarks are bound to that. That means these quarks must have to be in certain position to exchange those gluons. Otherwise, those exchange of gluons can't be possible. And that's how the color field works. That means the force of color field works in this way, that quarks are exchanging in the speed of light some particle named gluons, which have the color quantum number of anti-red, anti-blue, anti-green, and those things. So these are the things I have learned in quantum chromodynamics theory. If you like this, you can share your recommendation in the comment section, and if you like this kind of videos related to physics, feel free to subscribe. It's absolutely free, and press the bell icon beside the subscribe button so that you will be notified when the next time I will be uploading this type of interesting video for you. So that's all for today, and bye bye. See you again in some other kind of videos like this.